Okay, so for this example, we're going to be working on a polar area problem, and we're just going to be paying careful attention in all of our polar examples to really notice what order the curves are graphed and be careful about that step of this. So for this example, we're going to sketch the curves r1 equals 4 cosine 2 theta and r2 equals 2. And we're going to be trying to find the region that's outside the rows and inside the circle. We're going to write an integral expression to compute the area, but we won't actually integrate it. We're just going to try and break down what integrals would give us the area that we're looking for. So at this step, it will be helpful for you, if you do have graphing technology, to grab that to walk you along the graphing process a little quicker. I know that R2 equals 2, that our R2 is going to be a circle with radius 2. So that one's a little simple to graph. And it's going to be plotted counterclockwise. Okay. So there's our R2. And our 4 cosine 2 theta, let's use a different color, is going to be a rose. Okay, so when the rose is graphed, its maximum petal length is going to be 4. So it's going to start here, and it's going to come around. And graph half the petal. And then it's going to come down and graph this part of the petal, and then it comes around. And then it does this half petal. Then it does this half petal. Then it does this half petal. Then this one. And then finally it closes the loop over here. Okay, so paying attention to the order that this is graphed is going to be very important, because when we sweep the curve, we're sweeping where the curve is plotted. So even though things visually look like they were plotted at a particular theta value, that's not necessarily the case, right? So it was the case that the curve was plotted, like the petals were plotted in halves. So when we actually calculate the area that's happening between these, we want to stick with areas that we for sure know we're sweeping. So we don't want to cover too broad a region of theta values. Okay, so the area that we're trying to find is, let's shade it in green. We're trying to find the area outside the rows, inside the circle. Okay, so a little green part. Okay, these are not just straight up circular wedges, because notice the sides of them are going to be the flower petal. So there's several different ways that we could tackle this area, but I think it's safe to say we see a symmetry happening, and we can take whatever area we find in the first quadrant, multiply it by 4, and then that'll give us the total area. So right away, we're going to focus on first quadrant. Green area. Okay, so the 4 multiplying out front is to handle the fact that this phenomenon is going to happen in 4 quadrants. So the way that I would probably go about doing this is I would probably take the area from this intersection point to the center, and I would find let's draw attention to it in red. I would just find this area, red and blue. Okay, so as my circle is graphed from 30 to 45 degrees is when the petal will be back at the origin, and 45 is when this circle is halfway through. So I know that on that quadrant, this area is completely going to be having the circle being outer and the petal being inner. So when I set up my integral to find the area between the two curves, there was no switches of one of them being inner, one of them being outer. So I'll do 4 times, and then there's going to be 2 halves to each of these green regions. So 2 of them. So just one of them would be this orange area here. So keeping my color coordinating the same, we would go from pi over 6/30 to pi over 4. And remember, the formula is 1/2 the outer is the circle minus 1/2 the inner, which is the petal, squared d theta. Okay, and again, there were 2 of them because there's 2 halves to that region. Okay, so I think this is the easiest integral. I think this is the easiest way to find that region directly. There's a whole bunch of interesting other geometric ways that you could go about doing this one. In terms of, like, you could view it as having the whole first quadrant. You could start with a quarter circular area and then take away the inner parts of the rose petals right here. Some people can definitely see it that way. I've definitely seen some other interesting things, but again, I think this is probably the simplest way to go about it. So this, for me, satisfies what we're trying to find here. And then from there, you could just simplify it and use some trig identities for the double angle to integrate. But we weren't asked to integrate for this one, so I'll just leave it at that. Hopefully this was helpful.